Good evening, friends. Welcome to our webinar on how to produce a disease-suppressive soil. This is a topic that I've gotten a lot of questions about for the last couple of years and been trying to learn more about and trying to better understand how to develop more disease-suppressive soils. And I've been looking forward to the discussion tonight to share some of the things that we've learned. So developing disease suppressive soils is all about managing soil biology because disease suppression is a function of biology. However, intriguingly enough, the biology that develops a disease suppressive or the biology that has a disease suppression effect requires a specific biochemistry profile in the soil in order for it to thrive. Let's talk about disease suppression. I was very intrigued. The term disease suppressive soil, if I'm not mistaken, stems back to the late 60s when the American Phytopathological Society first published a small pamphlet on developing disease suppressive soils and some of the characteristics of disease suppressive soils. So I want to speak a little bit about some of those pieces. The foundational premise behind developing disease suppressive soils is really goes back to the history of Louis Pasteur versus Enderlein in France when Pasteur first developed the germ theory. The germ theory being the idea that we have a specific organism that causes a specific disease. And Enderlein was an advocate of the idea and the hypothesis that the development of a disease and the expression of a germ and of a potential pathogen is really dependent on the terrain. It's really dependent on the environment that is present. So the idea that he advocated and expressed was that even though you have the presence of a potential pathogenic organism, that organism may not necessarily express itself as a disease if you have a disease suppressive environment. And we do know now, over the last number of decades and centuries, the research that has extended us since then is that obviously there are specific organisms that cause specific diseases, as we know very well. And also, those organisms can and are, in many cases, abundant and prevalent in the environment, but still don't cause an infection when the environment in the host is not conducive to causing an infection. So the idea of developing a disease suppressive soil is the idea that we can develop an environment in the soil profile that doesn't provide the nutritional or biochemical environment that pathogens need to express themselves. There's other characteristics as well to developing a disease suppressive soil, but I want to talk a little bit about some of the biochemical profiles and some of the things that I've learned in the last couple of years. I found it really intriguing, a conversation with Don Huber a couple of years ago when he described for me the very first time, he said that the population of Fusarium has no bearing on whether there will be a root system infection. And in fact, when you have two fields side by side and one field has an infection with Fusarium and the next field right beside it does not, the Fusarium population in each gram of soil can be identical. There isn't necessarily a difference in the population of Fusarium in the soil. There is simply a difference in the rate of infection based on the other characteristics that are present in that soil profile. When Don described this, he also described a really interesting historical story of how they used disease suppressive soils to manage diseases in potato production in Idaho. So the foundational idea of managing the soil's biochemistry environment to develop disease suppressive soil is reduced versus oxidized soil environments. So reduced environments tend to generally be disease suppressive. Oxidized environments tend to generally be disease inducing. So when we begin speaking about reduction versus oxidation, this is unfamiliar terminology and unfamiliar language to many growers and agronomists. You may have heard of it with other terminology such as redox. Sometimes we hear people talking about redox or occasionally reduction oxidation. Sometimes ORP. Some people may be familiar with ORP meters, which stands for oxidation reduction potential. So there's different terminology that is used to describe this, and I want to just offer a bit of a synopsis on the terminology and what it really means and how it can affect us. pH and EH were originally mathematical symbols that were developed, or I should say physics symbols that were developed to represent proton pressure or proton transfer potential in the case of EH, and electron pressure or electron transfer potential in the case of EH. So we know many of us are familiar with pH having a scale from 0 to 14 with a neutral point of 7 and being a measurement of acidity versus alkalinity. And then on EH, we have a scale from 0 to 42 with a neutral point of being 28, measuring reduction on the bottom of the scale, a reduced environment, or oxidation, oxidized environment on the upper end of the spectrum. So I want to talk a little bit about what oxidation and reduction really are from a biological perspective and the impact that they can have on developing a soil's disease suppressive characteristics. So there has been this idea, particularly within the domain of biological and organic agriculture, that really healthy soils need to be aerobic. We need to have aerobic soils, and aerobic soils are good, and this also extends to composting and compost tea. Aerobic soils are good, aerobic compost is good, anaerobic compost is bad, and anaerobic soils are bad. Scope of the conversation up to this point has been distinctly black and white, good versus evil. It really isn't that simple. The reality is, when we look at the evidence that is presented, the really healthy soils, Gabe Brown described it very, very well recently in a conversation that healthy soils are actually a subaquatic environment. Soil biology lives in the water films that is on the soil colloid, which essentially is a subaquatic environment. What soils really need is not to be aerobic in the context of having a high oxygen content. Instead, healthy soils need to have a good gas exchange. Having good gas exchange and being able to diffuse gases across the soil surface, both releasing carbon dioxide into the atmosphere and absorbing oxygen and nitrogen gases into the soil profile, is very important. We don't necessarily want a high oxygen content in our soils. We need to have good gas exchange. Those are two very different things. However, so when we look at the different types of biology that thrive in different environments, we can see that there's actually 3 different groups of biology, not just 2. So for the sake of this discussion, I'm going to focus specifically on bacteria because they are one of the more abundant populations in the soil profile. They are the most abundant in terms of biomass. So you have some bacteria that are referred to as being completely aerobic. Aerobic bacteria are dependent on an environment that contains some oxygen. They have to have oxygen present in order for them to thrive and survive. And those, of course, when you have oxygen present, you're going to have a slightly oxidizing environment. So it will be slightly above the neutral point of 28. Then you have other bacterial organisms which are completely anaerobic. They cannot survive in the presence of oxygen, and they're dependent on having a completely anaerobic environment. So these microbes are the ones that when agronomists and soil scientists talk about the negatives of anaerobic soil microbial communities, microbes that produce alcohols and such as ethane and methane, et cetera, and damaging soil compounds to the soil profile, these are the group of microbes that they're talking about, those that survive in an extremely anaerobic environment. But then there's a third group, This third group of bacteria are referred to as facultative anaerobes. And what that means in plain English is these bacteria can thrive in both slightly reducing and slightly oxidizing environments. They can cross the threshold of the neutral zone. So they can live in environments that have a small amount of oxygen present or that are slightly reduced, but they can't thrive in the extremes on both ends of the spectrum. The interesting part is that generally speaking, the bacteria which have a disease suppressive effect and suppress pathogens from causing an infection are all of these facultative anaerobes. They're not the aerobic bacteria, and they're not the anaerobic bacteria. They're in fact the bacteria in the center zone, these facultative anaerobes. So why does all of this matter, and how can we manage it, and how can we impact it on our farms? Well, I'd like to share a story of potato production in Idaho, a story that was originally related to me by Don Huber. Don described how in the 50s, 60s, and 70s, before the widespread introduction and use of fumigants and fumigation, in the potato production region of Idaho, they had three major diseases, soil-borne pathogens. They were Rhizoctonia, Pythium, and Fusarium, if I recall correctly. I think it was those three. So they were successful in developing a treatment method for controlling these diseases by developing a microbial profile, a bacterial profile in the soil that had a very strong disease suppressive effect without using fumigation. So their technique, their management practice, they had a 5-year rotation with potatoes 1 year out of 5. The 2 years prior to going into potatoes, they would plant a crop of alfalfa and harvest alfalfa for 2 years. The spring of the 3rd year, they would incorporate the alfalfa, allow it to grow about 2 feet tall, and then plow it down. So for a little bit of context, in these potato production regions, the soil is relatively sandy, and there is predominantly, even today, there's still a lot of flood irrigation, and then in that time period, it was almost entirely flood irrigation. The soils were so sandy and had such good water infiltration that when flood irrigated, they could go in to cultivate for weed control 18 hours after cultivation. They could go into work the fields. So the water moved through the soil profile very, very quickly. So they would plow down 2 foot tall alfalfa, 18 inches to 2 feet tall. And then immediately after they were done plowing, they would flood irrigate the entire field, and they would flood it until it reached the saturation point, and then they would leave it saturated for a couple of hours and then shut the water off. Doing that shifted the soil's entire bacterial community and developed a disease suppressive effect such that they did not have problems with Fusarium and Pythium and Rhizoctonia for 5 years after that treatment. Can you imagine that? They had a 5-year effect in producing a disease suppressive soil. So you begin asking yourself the question, I began asking myself the question, how did this work, and how were they successful in developing a disease suppressive profile that lasted for 5 years? What happened is, think about it this way. You incorporate a tremendous amount of biomass. So now you have all this alfalfa that was 20 inches tall, 2 feet tall, being incorporated. You have a tremendous food source for bacteria in the soil profile. So bacteria are going to begin breaking down all the alfalfa residue. Now, they flood irrigated the field, and the soil is completely saturated. So when it's completely saturated and flooded, you've now produced a anaerobic environment that is not going to allow the oxidizing bacteria or the aerobic bacteria to survive. So now you've eliminated the aerobic bacteria at the top of the zone. The aerobic bacteria are not going to be present anymore because of the flooding. So now you allow the flooding to remain and continue, And then after 4 to 6 hours, the water dissipates, flows out through the soil system. And now when you allow airflow and oxygen back into the soil, remembering again that this soil was just plowed and it's very sandy to begin with, so you have good air exchange and good gas exchange. When you've introduced oxygen back into the soil, you've created an environment that the completely anaerobic bacteria at the bottom of the spectrum can't survive anymore. So the only thing that you have left, the bacteria that are now going to consume the alfalfa and use it as a food source, are the facultative anaerobes in the center of the column. For the sake of discussion, to add some numbers to this, if we go back to this slide, you've now eliminated the aerobic bacteria and the anaerobic bacteria. So let's just say for the sake of discussion that before the alfalfa was incorporated, you had a soil, these sandier soils, because of good gas exchange and being fairly aerobic, might have had 70% aerobic bacteria and 20% facultative anaerobes and 10% anaerobic. And obviously there's shifts and changes at different levels and different depths of the soil horizon. Now, following the incorporation of the alfalfa, plowed down, and following the flooding treatment, after a bit of time to digest and consume the alfalfa crop residue, you may have completely changed that environment. Now, it may be 5% aerobic and 90% facultative anaerobes and 5% anaerobic. So now you have the majority of the bacterial population in the soil profile being these disease-suppressive facultative anaerobic bacteria. This is how they developed a disease suppression effect that lasted for 5 years after a single treatment. So now we need to ask the question, how can we replicate this and how can we produce this effect? Many of us, we don't have flooding. We don't have the option to flood our fields. So how do we produce the same effect that they were able to produce? And the key is that there are two different ways of producing this effect and shifting the soil's microbial population based on what is happening in the soil profile. So I want to talk a little bit, before to provide a bit of context for this, I want to talk a little bit about redox and EH and what it actually is and how it works. So with redox, we have this scale, reduction oxidation. We have a scale from 0 to 42, and the neutral point is 28. Now, you should be asking the question, why have you not heard about redox before? Redox or I should say maybe perhaps EH, ORP, actually has a much bigger impact on nutrient availability than pH does, particularly for all the trace minerals. Manganese, copper, iron, cobalt, etc., are extremely EH dependent. So why is no one talking about this? And why isn't there more research and more information available about EH and about soil ORP? The reason that this is not widely studied and described is because it's such a difficult number to measure. It's what I refer to as a wobbly number. It moves around all the time. And it moves around because of the many different things that impact EH. So just the environment, when you have anything that is going to increase the weathering effect on soil, such as tillage or drought, whenever you introduce high concentrations of oxygen into the soil, it's going to have an oxidizing effect. So when soils dry out, they become more oxidized. When they become flooded and saturated, they become more reduced. So in terms of actually measuring the biochemistry is constantly fluctuating. It's moving back and forth. It's a bit like it's trying to study a moving target because the number fluctuates so much, which is why it's been difficult to study and difficult to analyze and report about what's actually happening, what's actually going on. So as you can see on the upper left, there are a number of different applications that can have a strong oxidizing effect on the soil profile. There are nitrate applications, limestone applications, fertilizer, most salt fertilizers all have a very strong oxidizing effect. And what this has resulted in, many of our modern management practices have tended to have a very strong oxidizing effect on the soil, which has resulted in soils which have a disease enhancing rather than a disease suppressive effect. And I want to talk about how we can flip that around and how we can balance these scales. It's not about a need or desire to have completely reduced soils, because the number is supposed to wobble for a reason. Healthy soils and healthy ecosystems will naturally have this fluctuation and transitions between slightly oxidized and slightly reduced. It needs to be a fluctuating number. It's not healthy if it's a static number. So it needs to be moving. The challenge is that so many of the things that we do as farm managers tend to have a very strong oxidizing effect. We can see that there are things that we can do to help tip the balance back to the reduced end of the spectrum. We can, one nutrient that has a reducing effect is ammonium. And then of course, soil biology and root systems. And I want to speak a little bit about those as well. So the key piece is to remember that disease suppression in soil profiles is an effect of soil biology. It's a biological effect. The other things that we do that as farm managers, whether it is application of fertilizers, application of limestone, tillage, moisture management, etc., when those have a disease suppressive effect or a disease enhancing effect, it's because of their effect on biology and how biology responds. It's not because of a direct effect from the chemistry changes in the soil profile itself. So biological profiles and shifting the proportions of these three populations, aerobic bacteria, facultative anaerobes, and anaerobic bacteria, shifting these populations can happen in two different ways. One is, well, actually there's more than two ways, but the two primary ways, the two major ways in biological farming systems is one, they can be altered by the redox levels in the soil profile. So all those management tools that I mentioned or that I referenced can have an impact. Or we can also alter the biological profile by managing the crops and the cover crops that we are growing because of the different bacteria that they have a symbiotic relationship with. So we understand and we know that specific diseases, or excuse me, that each crop has a group of bacteria that it will have and other organisms that they have a symbiotic relationship with. So some plants have symbiotic relationships with groups of bacteria that tend to have an oxidizing effect, and others have a symbiotic relationship with groups of bacteria that have a reducing effect. So actually, let me describe that for just a moment. So far in the conversation, I've been describing how reducing environments or oxidizing environments can shift the bacterial population. But in fact, there are bacteria that can have a reducing effect or an oxidizing effect. And the way this is somewhat environment determined, but it is also crop determined. A bacteria which has a reducing effect on minerals in the soil profile. So we have all these minerals, manganese and iron, copper, cobalt, and so forth, all these trace mineral metals, phosphorus, sulfur, nitrogen. They can be in an oxidized form or in a reduced form. And when you have soils that primarily have reducing bacteria in a reducing environment, they will use electrons from these minerals and convert them into the reduced form. Bacteria are the mediator between what happens in the bulk environment from a biochemistry perspective and what happens to minerals in the system. So bacteria can convert trace minerals and nutrients to either be in the oxidized form or in the reduced form. You want to have bacteria that convert minerals to be in the reduced form. And this is important for nutrient absorption, which is a whole other conversation in and of itself. But the important point that I want to make is that each crop or cover crop has symbiotic relationships with either reducing or oxidizing bacteria. So they will shift soil and the soil's microbial community to either become more disease suppressive or to become more disease enhancing. So the challenge with many of our farm management practices today is that we do many things which tend to have a very oxidizing effect. We apply limestone, we apply nitrogen fertilizers, many farmers still till their soils. So many of the things that we do have an oxidizing effect, and many of our soils are overly oxidized. They no longer have enough reducing effect in the system. So our desire should be to bring some balance to that and try to balance out that scales by having more of a reducing effect and growing crops and cover crops that will stimulate the reducing bacteria, not the oxidizing bacteria. So what are some of those crops? Crops that have a symbiotic relationship with disease suppressive bacteria. There's a small handful that we know of that are exceptionally noteworthy. And then there are many more that we still have limited information about and that we're still trying to learn more about. So the first one crop that has a very strong reducing effect is non-GMO corn. And specifically, I'm making specific reference and mention to the non-GMO characteristic. And the reason for this is because non-GMO corn has a very different amino acid profile and carbohydrate profile from GM corn, which the altered, when you have genetically modified corn, the altered amino acid profile and carbohydrate profile that is sent out through the root system as root exudates results in an altered microbiome. And the GMO corn plant actually will have a microbiome of disease enhancing bacteria that tend to be an oxidizing bacteria instead of disease suppressive. Forage legumes, alfalfa is particularly noteworthy for having a disease suppressive effect. Also clovers, sweet clovers, crimson, red clover, white clover, carrot clover, et cetera, et cetera. All the forage legumes that I'm aware of tend to have a strong reducing effect and a strong disease suppressive effect. Amongst the grains, we know that wheat is particularly oxidizing. In fact, again, I don't know, there's not a lot of information. I've looked hard for more information on the various grains. I have not been successful in finding much information on barley and rye and spelt and many of the other small grains. I do know that wheat is particularly oxidizing and has symbiotic relationships with oxidizing bacteria. As far as I know, oats are the only small grain that have a strong reducing effect. And there's actually a really interesting story with oats that was related to me by someone connected with the breeding work many years ago. It's my understanding that prior to, I want to say, the mid-60s, oats also had an oxidizing effect. All the grains had an oxidizing effect. But there was a disease outbreak in oats, and the name is escaping me at the moment. I want to say gray leaf spot or something like that, but I'm no longer entirely certain. And this disease was very widespread. It decimated the crop across all of the North American continent for 2 or 3 years in a row. Breeders were working very actively to try to develop resistant strains, which they were eventually successful in doing. These resistant strains became quickly adopted across the entire continent. And these strains, these resistant strains of oats, were resistant to the gray leaf spot because of increased and higher concentrations of glucosinolates in the plant sap. And those higher concentrations of glucosinolates resulted in, when those went out through the root systems as root exudates, they resulted in an altered microbiome that switched the microbiome from a primarily oxidizing to a primarily reducing effect, which I find to be really intriguing because it definitely speaks to how the nutritional profile and nutritional integrity of a plant, as reflected in epigenetic expression, can change the microbial proliferation in the soil. This GM versus non-GMO corn actually would be an example of the same thing. Buckwheat is another cover crop that is known to have very strong disease suppressive effects. So those are the crops that we actually know that they have a disease suppressive effect and that they have a reducing effect on that the bacterial symbionts have a reducing effect. Crops that are particularly oxidizing that we know of are GM corn and wheat and GM soybeans. Everything else, if you were to ask me about it, I would have to say we don't know. I have suspicions that perhaps brassicas and mustards may also be reducing, but I don't know that for certain. There's still a lot of information missing and a lot of homework that needs to be done in those areas. Those are the thoughts that I wanted to share regarding what we've learned about how to develop disease suppressive soils. I'd like to open it up for any questions that you might have. While I wait for some questions to come through, I'll perhaps speak just a bit more about reduction and oxidation. So what is oxidation? Many of us understand what oxidation is. Oxidation is the natural weathering process that occurs in the presence of oxygen and sunshine, etc. When you expose a piece of metal to the air and it starts rusting, that's oxidation. So the opposite of that is, let's say you take that piece of rusted metal and you dip it into, let's say vinegar, apple cider vinegar. That piece of oxidized, that rust is going to come off and the metal will become bright and shiny because all that rust will convert back into reduced iron in the vinegar because vinegar is a very reduced environment. So examples of highly reduced environments would be corn silage or sauerkraut or apple cider vinegar or yogurt or a blueberry bog or a rice paddy. What do those have in common? They are all environments in which you have anaerobic fermentation. So those are all highly reduced environments. And when you think about it, if you think about just nitrogen as an example, so blueberry in a blueberry bog and in a rice paddy, you have a very anaerobic environment. And I made reference earlier very briefly to that the anions and many of the trace mineral metals exist in the soil in either the reduced or the oxidized state. So in the case of nitrogen, you can have reduced nitrogen or oxidized nitrogen. Oxidized nitrogen is nitrate, NO3. You have oxygen partnered with the nitrogen to form nitrate. So when you have a very reduced environment, reduced nitrogen is ammonium, NH4. And blueberries and rice are both dependent on absorbing the majority of their nitrogen in the form of ammonium because they are natively adapted to living in a very highly reduced environment. This is another example. Speaking of blueberries, there's a lot of discussion about the importance of blueberries having an acidic pH. And it is true that blueberries do thrive in an acidic pH, but in reality, what blueberries need equally as importantly, or I would even suggest more importantly than acidic pHs, is they need a reduced environment. Because in a reduced environment, you have exceptionally high availability of manganese and iron in the reduced form, and phosphorus in the reduced form, which are the three nutrients that blueberries have very high requirements for. And you also have nitrogen present in the form of ammonium. So I think the conversation historically around a soil's biochemistry has revolved principally around pH, and we need to expand that discussion, also look at EH as well. So we have a number of questions coming in. Thank you, guys. Anthony Granatelli. Good evening, Anthony. What do we know about types of weeds and their effect on oxidation and reduction? I wish I knew the answer to that question. Based on the fact that, so I think we can partially answer this question by looking at the environments that weeds thrive and survive in. So you have this one group of weeds that grows in tilled soils and in tilled environments, lamb's quarter and redwood pigweed and et cetera, et cetera. You know the list. I would anticipate that those weeds, obviously they appear to thrive in an oxidized environment. And often weeds are present because they are nature's correction mechanism. They're there to try to bring balance back into the ecosystem. And so I would expect it's possible that they have a reducing effect on the soil environment. I don't know that for certain. That's just a hypothesis and kind of an educated guesstimation, if you will. And then you also have these weeds which grow in obviously compacted soils, which have poor gas exchange. An example would be bindweed or quackgrass, twitch, or whatever local name you may know it be. So when you have, and there are many weeds that also grow in these very compacted soils. So I guess my expectation would be that weeds are generally trying to bring balance to the system. So it's really a question of what environment are they growing in, and what would be the counterbalance to that. That's my best guesstimation at this point. Sorry, I'm not able to answer it better. Sarah Goldberg asked a question. Hi, Sarah. How might EH and pH be related? You mentioned an example with sandy crops, which I understand to be acidic. How might EH effects be different in less sandy soils? Has this been tested? So, Sarah, this is a very good question. What I can say in general, so first of all, EH and pH are not necessarily correlated. You can imagine a chart that has EH on the vertical axis and pH on the horizontal axis. And then you can draw a line through the chart where the neutral points are. And that will give you 4 quadrants. So you can have a quadrant that is acidic and oxidized, and a quadrant that is acidic and reduced. You can have another quadrant which is alkaline oxidized and alkaline reduced. There's some really interesting work that I'll be presenting at the Acres conference that was done by Louis Claude Vincent in France in the 70s. And he developed these quadrants, and he termed his research bioelectronics. And he identified that there was a specific region in this EH-pH quadrant that was an optimal environment for a given plant or for a person, if you were measuring their blood, for example. And then each of these 4 quadrants, one quadrant, if you were predominantly in one quadrant, that it expressed that you had the potential for a viral infection. A second quadrant, you had a potential for bacterial infection. A third quadrant, a potential for fungal infection. So he was actually able to separate out the different types of infections based on the bioelectronic environment that you were in as he was measuring using pH and EH. So they don't necessarily correlate. With that being said, in biological systems, there often, when you have biological fermentation, there tends to be an association between acidity and reduction. So often, and particularly, specifically, I should clarify, specifically when you have an abundance of food sources. So when you think about sauerkraut or corn silage or yogurt or any of these environments that I mentioned, they are very acidic environments as the result of microbial metabolites. So the fermentation process produces all these acidic compounds that lowers the pH. And So there's often the correlation between a reduced environment and an acidic environment, but it's not a universal, it's not necessarily true. Tessa Graswitz shared a comment. Thank you, Tessa. Glucosinolates are common in brassicas. You might expect the latter to promote reducing bacteria as in the disease-resistant oats. Yes, that is correct, which is why I made the comment that I suspect that brassicas are also reducing, but I don't have any documented evidence to verify that that is actually the case. And the same also holds true of mustards as well. You would expect the same would be true of mustards also. Kenneth Peters, lately, no-till has been very much in vogue. You talked about plowing down alfalfa, but on a slide, it said it's oxidizing. Could you explain when to till and when not to? Okay, I may have made a mistake on the slides. Alfalfa is not oxidizing. Alfalfa has a very pronounced reducing effect and is very strongly disease suppressive. So just to clarify that, that may have been misunderstood, or maybe I made a mistake, in which case it needs to be corrected, but alfalfa is not oxidizing. So could I explain when to till and when not to? From a disease suppressive and a soil health perspective, I would say that optimally, from an idealistic perspective, and this is, of course, I'm specifically with that caveat in that framework, from an idealistic perspective, the only time that I would endorse and encourage tillage is when you have obvious soil structure issues which need to be addressed. And you have soil compaction, when you have very anaerobic environments that you need to disturb the soil, that is an appropriate time and place for tillage. Otherwise, I believe the ideal is to develop a soil environment from which you've removed the compaction, you've resolved those problems, and then to not till. Because as I described, optimal soil environments are slightly anaerobic. Disease suppressive soil environments are slightly anaerobic, not extremely anaerobic, but they're slightly anaerobic. They are optimal pH is slightly below the neutral point of 7, 6.4, 6.2, 6.8, etc. That's optimal soil pH. Optimal soil EH is also slightly below the neutral point, slightly below 28, ranging in the range from 24 to 26. So we want soil environments to also be slightly reduced. Lawrence Pasiniak, good evening, Lawrence, asked the question, would planting buckwheat in the rows of an apple orchard help with the reducing effect? The answer is absolutely yes. Any cover crop that you can plant between the tree rows, that any of those cover crops that I identified that I mentioned, so oats, buckwheat, forage legumes such as alfalfa, all will have a reducing effect. And still a bit early for me to say with a lot to say definitively, but it seems when we grow a series of these very disease suppressive cover crops, they may be able to overcome replant disease, which is a really big deal, something that's very important. Thanks, Lawrence. Great question. Anthony Griffith asked the question, you mentioned that legumes like clover, for example, are soil reducing in nature, but they encourage pests like nematodes. How do you reduce pests like nematodes in a reducing environment? Anthony, this is an awesome question. Thanks for asking this question. Here's the answer. Nematodes will only feed on legumes when the legumes are in proteolysis mode. In other words, when they don't have complete proteins, which means that this will happen when legumes are in an environment where typically they do not have enough trace minerals. The two that are most prevalent and most common, or actually I'll expand that to three, would be molybdenum and cobalt and boron. So often when you supply adequate levels of molybdenum and cobalt and boron, nematode populations will virtually vanish. So from my perspective, a nematode problem is a nutritional problem. You can solve nematodes with nutrition. And then when you use those as a cover crop, you can now also have all of the reducing effects that you are looking for in developing a disease suppressive soil. That's a very good question, Anthony. Thanks for asking that. Another question, how can I test the EH in my soil? You can, it's really inexpensive, and it doesn't matter. It sounds crazy for me to, it may sound crazy for me to say that, but here's the interesting part. It's not about the chemistry that's in the soil, it's about the biology. So the challenge with measuring EH is it moves so quickly. If you have a week of warm, dry weather in August and your soil dries out and starts cracking, it's going to test as being extremely oxidized. If you then get an inch and a half of rain and your soil becomes saturated, it's going to test as extremely reduced as little as 10 hours later. So the number can move very rapidly, very quickly back and forth. It's not about what is the EH in your soil. The more important question is your bacterial population primarily reducing or primarily oxidizing? That's what you should really care about. And the only way you can shift that is by shifting your crop rotations and your cover crop rotations to make sure that you have primarily reducing crops and as few as possible oxidizing crops. That's really the answer. That's really what you want to achieve. Greg Pennyroyal. Good evening, Greg. Glad to see you here. Question regarding tillage. Is tillage to open up compacted soils and increase gas exchange more beneficial than the potential oxidative negative effect? The answer is yes. There is a time and a place for tillage to open compacted soil, and because really you can think of it kind of as a two-step process. Before you can develop a population that is dominated by the facultative anaerobes, you first need to have good gas exchange. So good gas exchange comes first, facultative anaerobes come second. You won't build populations large of predominantly facultative anaerobic bacteria until you have opened up the soil and have good gas exchange. So there is a time and the place for tillage and for deep ripping soils. Sebastian asks a couple of good questions. Like to see non-anecdotal evidence. Some of the claims made here: facultative anaerobes suppress soil-borne diseases. GMO corn has an altered amino acid profile, changes the redox status compared to non-GMO corn. Could you please provide the sources of this information? Sebastian, a lot of this information has come from peer-reviewed white papers that are mostly published by the American Phytopathological Society. So there's lots of their Congress proceedings, et cetera, that are available. And the information is scattered all over the place. I would have to dig for the specific references. They are out there. And everything that I've talked about has been published and peer-reviewed. So it is out there. I didn't reference it in the slide specifically, but I could go look for that. You can find that information. The American Phytopath Society is the best reference, and that would be the place that I would start looking. John Herrick asked the question, do you need to incorporate the alfalfa for maximum disease repression? So for maximum disease repression, the answer is yes. So think about what was happening in this story that I used as an illustration from the potato production. They were providing a food source for the bacterial population to proliferate. And then they shaped the environment by first flooding it and then letting it dry out. They shaped the environment to ensure that the only bacterial community that was present to really thrive and consume all of this biomass was the facultative anaerobes. So could you have had the same effect without that food source present? You could have shifted the microbial community a little bit by just consuming the root systems, but not near to the same degree that you were able to by having that soil, by having all that plant biomass present. So having the plant biomass present was required to shift the facultative anaerobes from 10% of the population to 80 to 90% of the population. You needed to have that food source there to allow that specific segment of the population to really explode. Walter asked the question, you mentioned testing results are difficult to depend on due to constant fluctuations. Is there any way to get an average EH over time and multiple tests? And how can we use those results to determine cover crop needs? You really don't need to do this, Walter. I don't care about EH over time. I don't care about EH in any given moment. What we really care about and need to care about is having a bacterial population that primarily has a reducing effect. And it's really very simple. None of our agricultural soils have bacterial populations that are predominantly reducing because of everything else that we do. We add limestone, we till our soils, we add salt fertilizers, we add nitrates. All these things that we're adding are having an oxidizing effect. So from a really practical perspective, we need to exclusively use cover crops that have a reducing effect to try to balance out all the other management things that we're doing. It's the only thing we need to do. The reality is that none of our soils have enough reducing bacteria. It really doesn't matter what the number is and what's happening. Our management practices at this point are all the way on the oxidizing end of the scale. So many of we've completely imbalanced the system by primarily doing things that have an oxidizing effect. We need to try to bring back some balance by using cover crops and crops that have a reducing effect only. Kyle Millett asked the question, why is oxygen correlated with electron configuration of ions? If I'm understanding correctly, oxidation is the tendency of ions to gain or lose electrons. So how does oxygen play into that? It's a very good question, Kyle, and you are correct. Oxidation is the tendency of ions to gain or lose electrons. And so oxygen only plays into that indirectly with the effect that it has on bacteria and the effect that it has on the anions, the major anions. So when you think about the anions, specifically sulfur and nitrogen and phosphorus can exist in the soil in these different oxidation states. And they actually swing the most widely. So if you think of the anions, for example, you can have phosphorus, well, let's lose nitrogen, which we already mentioned. You can have ammonium, which is reduced, nitrate, which is oxidized, and there you have the presence of oxygen. Same is true of sulfur, where you have sulfate, SO4, again, you have the presence of oxygen. And then, of course, there's also the effect of oxygen and the effect that it has on the bacterial population as well. So the bacterial population will use electrons in an aerobic environment. Bacteria will use electrons from oxygen. And in an anaerobic environment, bacteria will use electrons from manganese and iron, et cetera, et cetera. So it's also a biological effect that is happening. So there's both a direct and an indirect effect from oxygen presence. Tyler asked the question, just scanning and skimming all the questions that are here. It seems like my specific questions about rotations, et cetera, boil down to this essential question. When would you recommend using cover crops? I think, Tyler, the answer to that is very simple. Every single hour that you possibly have bare soil, you need to have a cover crop. You do not want to leave soils bare. You want to have soils covered with growing plants all the time. And so whenever you have bare soil, that's your opportunity to plant reducing cover crops. Sarah Goldberg asked the question, can soil eventually become too reduced? The answer is yes. And this is what agronomists have historically spoken about the downsides of soils that are anaerobic. So if you have soils that are very compacted, that don't have good gas exchange, or that are waterlogged, then they will become very highly reduced environments. And in those highly reduced environments, you have only the bacterial population present that is completely anaerobic. And yes, that does have a lot of potential downsides in producing, digesting and consuming organic materials, organic compounds, and producing alcohols and ethane and methane, etc. So it is possible for a soil to be too anaerobic. Anthony asked the question, does rye also have a strong oxidizing effect? I almost always get asked that question, and the answer is we don't know. I don't know. I wish I knew the answer, and I keep looking for it, but I haven't found it yet. And one last question. Anthony Griffith asked the question, Fusarium wilt tends to appear in waterlogged soils. Would soil reducing crops reduce the pressure of Fusarium wilt, for example, in such a case? Which cover crops are good for managing Fusarium wilt? So, Anthony, there's a couple of thoughts on your question specifically as it relates to waterlogged soils, because when you think about it, waterlogged soils are a reduced environment. I'd like to go back to something that I mentioned at the beginning, which is that disease suppression is really a function of biology. And so the cover crops that I mentioned, all the cover crops that I mentioned that have a reducing effect will help reduce will help create an environment in which Fusarium is less likely to be a problem. So buckwheat, oats, alfalfa, the forage legumes, non-GM corn, etc. Those are all cover crops that will reduce the virulence of Fusarium. And in addition to that, we also need to find a way to manage soil water and reduce compaction, or depending on what is going on in your situation, we need to make sure that your soils don't become waterlogged. Because when they become waterlogged, that does two things. One is it suppresses all the disease suppressive bacterial population that you've developed to some degree, the entire bacterial population for that matter, but it also weakens root systems. And so you still have this effect where you can have, just by having waterlogged soils, you can create a temporary disease-inducing environment because of compromised root systems and overall suppressed biology. So those cover crops that I mentioned would be valuable, but then you also need to manage the compaction and the water holding capacity issue. So those are all the questions for tonight. Thank you very much for all of you for contributing. I hope that you found it useful and enjoyable. I was very glad to have you here. Thank you for the interaction with the questions and the Q&A. And I look forward to speaking to you again on a webinar soon. Have an awesome evening. Thanks. Bye.